To truly master materials in Blender, you need to understand the flow of data. In this video for advanced beginners, we are going to explain the two core concepts that define that flow: pair point calculations and execution order. Understanding these concepts is far more important than memorizing what each individual node does when creating any procedural material. Let's start with the material output node. It tells Blender what the material should look like, or more precisely, it tells Blender's render engine how this object interacts with light. When we build a shader node tree, its final goal is to define the material properties, and all of these properties describe how the object reacts to light. Even color is one of these properties. When white light hits a red object, the surface absorbs most wavelengths and reflects mainly red, which is why we see it that way. That's what happens in real life, and that's exactly what Blender tries to simulate. Technically, when we create material using node trees, we are telling Blender's render engine that any object using this material should behave in a specific way when interacting with light. After we define materials, the render engine can calculate all the light bounces, reflections and shading to produce the final look of the objects and the entire scene. The material output node is the final step in the shader tree. It outputs all the calculate material information to the render engine. The surface input defines the visible color or shader of the material surface. For example, we can connect a simple RGB node, which always returns a chosen color, to see that color on the object. It can also take a single number or shader output as input. In Blender, colors are represented as RGB vectors, where each component stores how much red, green and blue light the color contains. The values range from 0 to 1. 0 means no light, and 1 means full intensity for that channel. When we connect a single number to a color input, Blender converts it into a three-dimensional vector where all components have the same value. Since all channels are equal, the result is grayscale color. You can think of 0 as pure black, no light at all, and 1 as pure white, the maximum amount of light. The surface input normally expects a shader, which technically describes how the surface interacts with light, combining multiple values and vectors to define things like reflections, roughness, metallic look, or transparency. But if we connect a color or a single value instead, Blender automatically converts it into a mission shader so it still works and produces a visible result. That's why we don't see a difference here. The material output node also has a volume input used for materials that fill a volume, like smoke or fog. For example, you can connect a Principled volume shader here to control how light passes through the material. If you look at the menu, you will see that Blender offers a huge variety of specific shaders for different effects. For example, there is a class BSDF designed specifically for reflection and transparency, or an emission shader which simply makes the surface emit light. But the modern standard that you will use for almost every material is the Principled BSDF. Think of this node as a smart converter. It takes a simple input like base color, metallic, roughness, or transmission and uses them to automatically calculate the physics needed to make the material look real. Internally, it calculates exactly how the light ray behaves. Primarily determines the direction and color of the scattered light, whether it reflects off the surface, gets absorbed, or enters the object. The result it outputs is a structured shader object, essentially a complete rule set that tells the render engine exactly how to simulate these light interactions. Since this video is about understanding the flow of data rather than memorizing every single button, we won't break down all of these 20+ parameters. Instead, we will focus on how we can feed data in these main inputs to drive the material's look. To clearly see the data flow and understand that rendering a material is a per-point calculation, let's quickly build a classical example node tree. Don't worry about the individual nodes if you don't understand them yet. We will explain them shortly. First, we have to stop thinking of the material as a static picture wrapped around the object. Instead, the secret to reading node trees is understanding that this is a per-point calculation. Let's pick two specific points on this cube and call them P1 and P2. When the render engine draws this frame, it has to calculate the color for every single point separately. Let's see what happens at point 1. The calculation starts at the texture coordinate node, which simply outputs the points' 3D coordinates. Each socket uses a different coordinate system, but they all just return position data. In our example, we are using the generated output socket. This tells Blender to define the coordinate space by finding the object's smallest fitting rectangular container, known as the bounding box. This box acts as the coordinate space, assigning 0, 0, 0 to the bottom left corner and 1, 1, 1 to the opposite top right corner. Based on this, the coordinates for P1 should be 0, 0, 1. If we switch to the object output socket, we are using the object's local coordinate space. This means the coordinate values will be based on the cube's origin point, giving us new coordinate readings. I will switch back to the generated socket. So when render engine asks what the color the P1 point is, we know that the texture coordinate node returns this vector, which is its position in the generated coordinate space. This vector then goes into mapping node. This node lets us adjust the coordinates by applying three basic transformations: location, rotation, and scale. Mathematically, location is simple addition, which shifts the coordinates. Similarly, rotation rotates the vector, and scale multiplies coordinates to stretch or shrink. If location and rotation are 0 and scale is 1, it returns input vector unchanged, as it is in our case. We will come back to the practical use of the mapping node shortly after we'll talk about the noise texture node. This new vector is then fed into noise texture. This is the most important part. The noise texture is simply a mathematical function. It takes the input coordinate vector, runs a complex formula on it, and returns a corresponding color value. The mathematical formula is designed so that if you take every single point in the 3D space and assign it the color value returned by the noise texture, it generates the characteristic random, cloud-like noise pattern in that space. And the good part is that you don't need to worry about that formula. However, you can change the parameters, which allow you to alter the shape of the function to change the final noise pattern. As we said, the function returns a color for a specific point in space. The factor output is its grayscale variant with values ranging from 0 to 1. This single value is later converted into a color vector at the base color input of the Principled BSDF node. Once the color for P1 is calculated, the engine moves to the next point, and it does the same for every single surface point, including P2. Finally, the surface is rendered, which is what we see on the screen. Let's back to the mapping node. Adjusting location in the mapping node shifts the noise pattern. It works by adding an offset to the input coordinates. This makes the noise texture function look up its value from a different spot in the 3D space, causing the pattern to slide. Increasing scale in the mapping node makes the noise pattern look smaller and repeat faster. It works by multiplying the input coordinates. This forces the noise texture function to cover a large portion of its internal pattern over a small area of the object, which visually compresses the pattern. To reset the node's parameters, first select the node and then press backspace. Now that you know the shader is calculated per point, let's formalize how the nodes are processed. This process is called the execution order. and understanding it is necessary to read any shader node tree. I previously said the calculation starts at the texture coordinate node and flows to the material output node. While this is generally true, describing it as a simple left-to-right flow is not precise enough. To show why, let's look at the new setup. Here we are using two new nodes in this example, the wave texture and the maximum node. The wave texture works just like the noise texture. It takes a coordinate vector as input and runs a mathematical function on it to generate a corresponding value. Instead of cloud-like pattern, this function is designed to generate a wave pattern in 3D space. The maximum node is very simple. It compares its inputs and returns only the largest value. When we are comparing two grayscale values, which are the factor outputs from our textures, it will always choose the one that is closer to 1, or the whiter point. By using this node, we are effectively merging the two patterns and ensuring that the final output color is always determined by the brightest part of either the wave or the noise texture at any given point. If we start reading from the texture coordinate and assume the execution order goes simply from left to right, it becomes unclear which node is next after the mapping node, noise texture or wave texture. Here is the main rule. A node cannot be calculated until all of its input sockets have received their final values. We know that the final node that needs to execute is the material output. But to execute that node, we need its surface input to be known. We can see that data comes from the Principled BSDF. So, to execute the Principled BSDF, we first need the output from the maximum node. Now, the maximum node is the key merging point because it needs two separate inputs calculated first. To get the maximum node's first input, we have to run the chain, texture coordinate, then mapping, and then noise texture. Yes, the texture coordinates executes first here, just like before. But to get the second value for the maximum node, we have to execute the texture coordinate and mapping nodes again, and then calculate the wave texture. Once both of these inputs are finally known for the maximum node, then and only then can we execute it. That result then makes the Principled BSDF input known, so we can execute that. And finally, the material output executes. To read any complex node tree, you must trace the flow backward from the final output to understand the sequence of dependencies. Hope that made sense. If you found this explanation helpful, please hit the like button and subscribe for more. Thanks for watching, and I will see you in the next video.